So far, we are able to solve the 8 distribution problems among 16 ones. So let's look at the next one, which says the number of ways to distribute n distinct balls to k distinct urn is given by k to the power n. So if we have to distribute the, so it's just like, distributing two different kind of chocolates to three different childrens, right? So here we can say that each of these different chocolates, we call it as like toffee 1 and toffee 2, and we have three childrens like C1, C2 and C3, right? So each of the toffee 1 can go to three places, right? So, and each of the toffee 2 can go into the three places. So by the multiplication principle, it will be nothing but 3 into 3, which is 3 to the power 2, right? So similarly, each of the distinct, each of the ball n can go into k places while distributing, right? So we have like n balls. So these are n balls, and for each ball, we have like k options where it can go. So it is like k, 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 and henceforth till n. So it is nothing but k to the power n. So you have seen the various kind of problems where this multiplication thing is used. So we are done with the one of the more things. So we have distinct balls and distinct urns, and there is no restriction applied here, right? So we have no restrictions here. So this is nothing but k to the power n. All right. Now let's go to the some of the different kind of problems. So we are now left with the 7 kind of problems, right? With no restrictions, and there is no urn is empty, and this kind of problems, right? So we are left with the 7 problems. So let's try to solve each one by one, right? So let's take an example of, let's say we have 6 identical balls which needs to be distributed among 3 boxes, right? So this is the case where you have 6 identical balls and we have 3 distinct urns, and there is no restriction is there, right? So we have no restriction out here. So let's try to solve this one and see what happens. Okay, so we have 6 distinct balls which needs to be distributed among 3 boxes. So let's represent these 3 boxes as this, right? Then this is box 1, now this is box 2, and this is box 3, right? So either you can put all the 6 boxes here, so you can put this six balls here and you place nothing here, right? Or what you can do is that again, right? So you can put 3 balls here, 2 balls here, and 1 ball here, because there is no restriction that each of the each of the boxes should have 1 or at most 1 or whatsoever, right? So now how we can find this distribution, how we are going to compute this distribution problem, right? So if you look at it, there is a bijection, right? So we'll use the bijection problem here. So here we can say the bars here, right? So these are like ones and these are like ones, right? Now if you pay a close attention, that this is represented at 6 zeros if we form a binary sequence, right? 1 2 3 4 5 and 6, and these 2 bars, which is the dividing the 3 boxes, are 2 ones. Similarly, this one represents three zeros, then one one, then two zeros again, right? And then one and zero, right? So it is, if you look, if you pay a close attention here, this is nothing but selecting the number of two ones from 1 2 3 4 5 6 7 8. Similarly here 1 2 3 4 5 6 7 8. So there is a bijection here, that it is nothing but selecting two ones from 8 digit binary sequence, right? So how we arrive at this? So there is a clear cut bijection. So if you know distribute anyways, you will find a binary sequence of 8 digit, and then you will have two ones, right? So let's try again. So these are three boxes which we have. This is one box, two box, three box. So you can put like nothing here, and then you can put like three balls here, and you have to put like five balls here. So there is nothing here. So we start with one, then we have three balls, which is three zeros. Then there is another one, and then we have 1 2 3 4 5, right? Oh, we have only six balls, right? Not, so we need to remove this three ball. So it is nothing but finding from 8 digit sequence, right? We have to find all the possible combinations where two ones are there, which is again pretty simple, is nothing but 8C2, right? So here what we have realized that via bijection principle we can solve this, right? Now let's try to find the final conclusion from where we have n balls and it needs to be n identical balls, right? Because identical is crucial here. If they are not identical, then these three zeros can be again arranged, and these three zeros can be arranged. And in the other cases it will be much more difficult, because there are so many cases. Here we have to arrange 3 2 1 and so forth. It will be really difficult, right? And so this n identical balls in three k distinct urns, right? So what you can do is that in case there are three urns or three boxes, you have seen that you can place a bar to distribute it, to break it into three different boxes. So one bar less. So always there will be k minus 1 bars here. K minus 1 bars will be here, right? And we have n balls to distribute, so there will be n balls, which are n zeros, right? So these are n zeros, and this is k minus 1 ones, right? So you can easily see that. So let's take another example to make it clear. So again we have, let's say, 5 balls and 5 identical balls, again sorry to say that, identical, and to 4 distinct boxes, or you can say urns, right? So the 4 distinct boxes can be framed by 3 bars here, which is k minus 1, right? And we have 5 balls, right? So we can put like 2 2 and 1, right? So again it will be same as we have a sequence of 8 binary sequence, 8 digit binary sequence, and we have to find that there are three ones, right? So if you write it generally, so we will write it formally now. If there are n identical balls need to be distributed among k distinct urns. The number of ways we can do is, as you can see here, so what we have done is that we have divided the whole urns into k minus 1 partitions, and then we are trying to find these ones, right? So this is nothing but it is nothing but n plus k minus 1, yeah, because n is the number of zeros and k minus 1 is the number of ones, and similarly we have to select the k minus 1 ones from there. So it is just the combination of it. Since the balls are identical here, there is no need of arrangement. So this is the formula for finding if n distinct ball needs to be distributed among k distinct urns and identical balls needs to be distributed, then the final conclusion is this, right? So let's take few of the examples to understand it better, right? So let's say we have we have 6 positive signs and 4 minus signs, right? Minus signs. Now we need to form a 10-digit sequence of these two 10-digit sequence. Okay, so now we are done with the one of the problems of the distribution. So let's write that into the table, back into the table, right? Let's write that back. Okay, so we will just, so it says that in an identical ball needs to be distributed among k distinct urns. So these are the possible ways, right? So we'll fill this up again here in our table. So we have identical ball and distinct urns, and there is no restriction. So this can be done. We know that can be done. So we have n balls. Again, I'll just write it here so that it's easier for you to remember, and k urns, right? So that can be done via n plus k minus 1, and this is the combination. Okay, so this is nothing but n k plus 1 c k minus 1, right? So let's take another one where each of the urn should have is not empty, right? Now let's say how we are going to do that. If each of the urn is not empty, right? So again, what we are going to do is that here, so we have filled that form. Now let's try to delete this. Okay, so we have again the k urns, which can be, so we have to draw the k urns here, or let's say 3 urns, and there are 5 balls, right, and 3 urns, and it says that none of the urn is empty. So basically at least one of the balls should be placed here. So one ball goes here, one ball goes here. So we are now left with the 2 balls, right, and which could be placed among these 3 urns again, right, because we are still left with the 3 urns. So it converts into the same problem. Instead that then we say that we need to now distribute the remaining 2 balls into 3 distinct urns, right? The problem remains the same here, right? So this can be done via 2 plus 3 minus 1, again 3 minus 1 ways, right? So we'll generalize this. So if n balls and identical balls balls needs to be distributed among k distinct turns wherein each urn each urn should have each urn is not empty, is not empty, right? So again you can do it by this way. So let's see that we have k urns. These are our k urns, or let's say 5 urns in this case, 5 urns, right? So it can be divided by 4 bars or 4 ones. Now each urn is not empty, so at least you have to put, and we have like say 10 balls, right? Again, so first you have to put one ball each into this 0 0, because it cannot be empty, right, as per our conditions. So now we are left with the 5 balls, right? So we are like left with the n minus k balls, and which needs to be distributed into k urns, right? K urns, and there is no restriction now, right? So it can be done via, you know, n minus k minus plus k minus 1 base into k minus 1 base, right? So this is nothing but n minus 1 k minus 1 combinations, right? Please note here the balls are identical, hence we don't need to, you know, rearrange the balls. So we finally come to this part. So here, you know, we have a condition that none of the urns could be empty. So we are done with this part as well, right? So it is nothing but n minus 1 and k minus 1. So let's try to take an example of it to understand it better. So I'll take an example of the problem from IIT and let's try to solve it using this concept, right? So the problem statement says we have 6 positive signs and 4 negative signs, and we need to form 10-digit sequence, 10-digit sequence of positive and negative signs wherein no two negative signs comes together, right? So this is the problem which has come into the IIT. So let's try to solve it, right? So what is the way of solving it is that first we place, so we have like 4 negative signs, 1 2 3 and 4, right? Since these two needs to be they cannot be together, none of the two, so there must be a positive sign here or a positive sign here and a positive sign here, right? And we are left with the 3 positive signs, 3 positive signs which needs to be placed into any of these 5 boxes, right? As you can see here, so you can put the positive sign here, 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 here. So there are 5 positive signs and 5 positive signs, 5 places where you can put all the positive signs, 5 places where you can put the 3 positive signs, right? So it drills down to the same problem saying that you have 3 balls which needs to be distributed among 5 urns, right? So we have put like 4 positive signs. So now 3 positive signs should be here because they cannot be together, right? But we are still with the 3 positive signs, and this could be placed among these 5 places, right? Or the 5 urns. So this will be nothing but 3 plus 5 minus 1, because there is no restriction. We have removed all the restrictions from here, and C5 minus 1. So that is nothing but 7C4, which is equal to 7 into 6 into 5 into 4 divided by factorial 4, 4 into 3 into 2 into 1. Now 4 and 4 gets cancelled, this 3 and 2 gets cancelled, so there are only 35 ways you can put. Please note here all the positive signs are same, so we can apply this principle to solve this problem, right? We are now done with the 11 parts out of the 16, and we are now left with the 5 more distribution problems, which I will be taking in the next session. For viewing more such videos, please subscribe our channel or visit our website deepdivemaths.com. Thank you.